You've probably already heard the news. On today, October 6th, 2025, it became public knowledge that the Enderlin, North Dakota tornado from June 20th of this year was upgraded from EF3 to EF5. This is a monumental moment in recent weather history as it becomes the first officially rated EF5 tornado worldwide in 12 years. So, how did this happen? And by asking that question, I mean, what meteorologically came together to allow a tornado of such intensity to happen? In this video, we're going to break that down. We're going to break down everything from the large-scale stuff, such as the low orientation and moisture advection pattern, and upper air advection, wind advection pattern, to the mesoscale stuff, such as nudgers and supercell scale things that helped a tornado of this intensity take place. First, you'll notice that it's June 20th, and June 20th is an important date because it's the summer solstice. So for the northern hemisphere, it's the longest day of the year, and it's the day that it receives the most solar radiation, and climatologically, it's supposed to be the hottest day. So it's no surprise that here, you have tons and tons of moisture lying around. This area, however, here, you can see there's a lot of low pressure there, sitting over the Rockies, which is typical Rocky Mountain cyclogenesis. Let's take a look. You can see some of that low pressure becomes defined, and becomes a clearly obvious low pressure system that zooms to the northeast and has a massive influence on moisture advection. Anytime, especially in summer, if you have a strong low pressure system, especially one of the 980s, right next to strong moisture, you are bound to get some interesting weather. But however, one important law is that the larger the low pressure system, or the stronger the low pressure system, the more influence it will have over moisture advection and things like that. Let's take a closer look at that here. So here, we're zooming in on the interest area. This area right here in North Dakota, this area I'm circling right here, will be our interest area for today. So this is zoomed in on the interest area. So you can see for the first 12 hours, not much happens, but then look at the bottom left. You can see the isobars clearly indicating that the low is beginning to arrive, and look at that rapid change. Remember how I said strong surface lows have such an incredible effect on moisture return? Look at how quickly that moisture return changes here. And here, now we have a really interesting warm sector, really good moisture, usable for severe weather, right next to a strong low. Oh boy, this is getting interesting. Now, let's take a look at the surface analysis map for 0Z. This paints quite an interesting picture. As like here, the area that I designated earlier as our interest zone is north of the stationary front and is not located relative to the low where you would expect a severe weather event to occur. You would expect a severe weather event to occur here in the warm sector, not to the northeast of the low. So why didn't this area do anything? Let's take a look at that. One of the most important parts when it comes to forecasting severe weather is to look at the upper air advection pattern. Where is that wind coming from? Where are the winds being advected into the warm sector or area of interest coming from? Because if you have dry air being advected into the warm sector, that is supercell kryptonite, and having dry air will hamper your chances at having significant convective activity. So it is incredibly important. So, two areas. Our interest area and our expected area. I'm going to use those terms going forward. So, let's look at the upper air, at the air going into the moisture. Let's look at the air going into the interest area. You can see, let's trace it back here. Trace the wind barbs. They're kind of coming from northern Wyoming. And let's take a look at the temperatures in northern Wyoming. You can see it's kind of dry, but dew point depressions here, they're like in the 30 degrees, so it's not overwhelmingly dry. So that's the air being advected into the warm sector. Now, let's look at this area, the expected area. Let's trace back. Let's start here, trace back. It's coming from southern Wyoming and northern Colorado. Let's take a look at the quality of the air coming from there. Oh boy, 93 degrees with a dew point of 24. The air being advected into the expected area is incredibly dry. It is incredibly, overwhelmingly dry, and that doesn't change. Here you can see 0Z, air still coming from northern, like South Dakota, and stuff like that. You can trace the wind barbs here. It's coming from the area which is still relatively dry, which is still relatively moist. I mean, dew point degrees of 30. Compared to the expected area, you're still getting air coming from here, where the dew point spreads are like 60 to even 90. What's 92 minus 18? To like 70 degrees. The air here is way too dry to get anything, and let's do a sounding comparison. Actually, before that, let's look at another thing. Temperature. At the start of the day, you'll notice here, if we go all the way back, you'll notice here that the expected air is already in the moisture pool. While here it's kind of cloudy and like there's not much moisture there to reduce temperature spread. Also, because it's for the north and where it was relative to the low, north in our expected area, north in our interest area, it was kind of colder. Like temperatures were in the lower 70s, while here in the expected area, they were in the high 70s. Because this area is already in the warm sector, and this area had much more time to destabilize during peak heating, especially during the summer solstice. So look, you see the temperatures rapidly increasing down here. Well, here, they kind of increase at the same rate, but they peak at lower temperatures. The temperatures in the interest area peak kind of in the mid-80s, while the ones in the expected area peak in the lower 90s. So you have mid-80s getting put with air that isn't so dry and getting massive moisture advection, as we saw earlier, or you have in the expected sectors temperatures in the mid to low 90s, which are having extremely dry air being advected into them aloft via the wind pattern. That's why that area was irrelevant. Let's do a sounding comparison. You can see throughout the day that doesn't change. In fact, it even increases the temperature near sunset. While here, as the sun sets, temperatures here begin to cool down. They're still in the mid-80s, and they're getting put with 70-degree dew points. While here, you're in the 90s, and you're getting slammed with the dry air from Colorado. Let's take a look. This sounding was taken here, South Dakota, which is in the middle of the expected area. Look at how dry it is. You have a good photograph, but I mean, that doesn't, and you have a lot of elevated instability, but that really, really does not matter. When you have that much dry air, it's going to be very, very difficult for you to get sustained, organized convective activity there. Let's compare that to one in the interest area. Look at how much less dry air there is, especially down here. There's just so much less dry air there overall. And ignore everything below this line, as this area is further north and has a higher elevation, and this sounding didn't account for that. But, I mean, you still have solid shear, you still have pretty solid wind shear, you still have a solid hodograph, and you have much less dry air. That's why you are far more likely to get convective activity in the interest zone rather than the expected zone. Now that we've covered it. So, this was the scene at 0C. And as our questions shift, so we're going to begin to shift from the large-scale pattern here to the mesoscale details. So, where would we expect storms to form? Look at these three images. Here's moisture, here's 850 millibar winds, and here's 500 millibar winds. So, where do you think storms are going to form? From here, given what we know, so first of all, this area over here is off limits because it's getting slammed with upper level air that is incredibly, incredibly dry. And because the air being advected here is so dry and moisture is also getting pulled away, this area is not going to happen. That leaves this area, our large interest area, for review. So 850 millibars is not going to help, which isn't surprising considering that lower level jets really wrap up later in the day, so ignore that for now. Let's compare that with 500 millibar winds. We know that the air being advected here from 500 millibars is moist and workable. However, when it comes to convective initiation, you really want to look at where stronger winds are aloft, because once you get updrafts to bust through, they're going to need some help get going up. You can see here, in this ring right here, there's an area of heightened 500 millibar wind speeds. And there's two areas. One right here, especially in this area, and second, there's kind of a smaller area ahead of this, we'll cut to the east of this interest area, where you can also see convective activity. So, I mean, you put them three together, you put moisture together, with upper layer winds, kind of one, I would expect storms to be in this area, and we expect storms to be in that area, and two, I would expect maybe a chance that you could get some discrete updrafts to form in this area. Let's check. Are we right? Perfect. You can see here a line of storms you can see here that there was a derecho beginning to take shape, and that was because that the vectors from 850 to 500 millibars really didn't change, so stuff kind of went up here and went linear really quickly. And also, most of the stuff wasn't surface based. As you can see, some of it's extending over here. So these storms are probably not going to be producing tornadoes. And then, as I said over here, remember, we had our heightened area of 500 millibar winds over here, coupled with workable moisture. Well, lo and behold, consider my surprise when we see an updraft developing. Let's see how that changes over the next few hours. You can see the derecho begins to move east, and this updraft kind of begins to gain intensity, and then, whoa, look at that jump. Another updraft goes up to the south, and within an hour and 30 minutes of the first image, you have a full-blown supercell here, a developing supercell here, and a full-on derecho. Now, obviously, the environment must have become favorable for supercells because, obviously, this supercell was able to go up and become very, very healthy within the span of an hour and a half. So, what was happening in the background parent environment in the interest region? We're going to go large scale for a minute. Look at this. This is a moisture for 0Z. One thing you will know, if you forecast severe weather enough, is that it's common in the plains or high plains for the LLJ to really ramp up as the sun sets. So that means lower level winds increase, and that increases both wind shear and moisture levels. Did that happen here? Well, you tell me. Let's fast forward 1 hour, Another hour, look at that change. You can see moisture significantly increase over the interest area. And by 3 UTC, our Warren sector, our area of interest is completely filled with 70 to 60 degree dew points. Let's look at the upper level winds. You can see as the LJ ramps up and as the system begins to pick up speed, look at how the upper layer winds significantly increase. Look at that conversion. At 0 UTC and at 4 UTC, look at how much stronger the winds are here aloft. That is going to make the environment much more favorable for sustained convective activity because you have upper layer winds to vent updrafts and to make them efficient. And let's look at the lower level winds, the lower level jet. Here, you can see here it starts 0Z, and then you can see as time goes on, especially the area of interest, it increases. It goes from virtually nothing to notably higher. It doesn't increase too much, but it does become noticeably higher. And look as that lower, so you had lower level shear significantly increasing, and actually that's my bad. One reason why this doesn't look so impressive is because like this here is higher elevation, but still the lower level shear significantly increased. How am I going to prove that? I'll show you two soundings in a minute concerning the Jamestown soups, concerning this supercell that will prove that. Actually, let me go to that right now. So this was at 1 UTC at about an hour before this supercell became mature. And look at that, and let's fast forward 1 hour. This is proof that the lower level jet was rapidly increasing. This is a 1 hour difference. Look at the photograph. Whoops, let me go forwards a little bit. Yeah, look at that difference. This is a 1 hour difference. Look at how much the lower level photograph was increasing. Okay, so now that we happened, this supercell has become mature. So we've established already that not only that the environment, that the parent environment in the area of interest is becoming more favorable because of the LLJ ramping up, increasing moisture, decreasing temperature spreads, and increasing lower level shear. So, as you can expect, you would probably think the supercell would be producing a tornado, right? Correct. It was producing an EF3 tornado at this time, thankfully avoided the town of Urbana, North Dakota. And this is the radar of the supercell at the time. However, a very interesting thing is that EF3 was the only intense tornado that the supercell produced. It produced one more EF2 and then stopped producing tornadoes entirely. Why is that? We've established that the background parent environment is becoming more favorable for supercells and tornadoes. So why did this supercell stop producing tornadoes after the Jamestown EF3 and then only produce one more EF2 here? And then why did it stop? Why didn't it begin to produce more and more insane tornadoes? This is where we shift back to the mesoscale side of things. This is at the time of the Jamestown EF3. Velocity equivalent supercell. You have our main tornadic supercell here and our secondary supercell here. Let's fast forward a bit. And then again, here's the sounding for reference. This is the sounding at the time of the Jamestown tornado. Keep this in mind, as not only did I use it to show you how much the lower level shear increased, I'm also going to show you why the Enderlin tornado was so much stronger than this one. Let's fast forward an hour. Here, you can see the northern supercell is kind of chugging along, but two things. One, the southern supercell is intensified a lot, and two, most importantly for tornado potential, the southern supercell's forward flank downdraft is getting into the way of the northern supercell's inflow. The southern supercell's forward flank downdraft is dropping stable air and forcing the northern supercell's inflow region to become filled with stable air. Stable air in a supercell's inflow region is tornado kryptonite. And as you can see, that southern supercell kept on putting stable air into that northern supercell, and eventually it just caused it to completely lose its identity as the environment became more favorable for that southern supercell. So let's look at the grand scale again and see what happens. Let's see this on the grand scale. Derecho obviously becomes much stronger and intensifies, but as you can see here, look, you see that southern supercell intensify. The FFD from that southern supercell begins to drop stable air into the inflow region of the northern supercell. That causes the northern supercell to lose its tornadic identity and overall lose its potential, while the southern supercell, which has nothing doing the same to it, is just free to kind of just vibe on its own and slowly intensify. Also notice one more thing. The QLCS is rapidly taking shape and has become extremely intensive by this point. By this point, the southern supercell is completely taken over the northern supercell because of a mesoscale process, which I'll get to in a minute, and the northern supercell's tornado odds are fried. And this is about 20 minutes before the Enderlin EF5 tornado formed. So, just a bit more context, so we know that the lower layer, that we know from our earlier discussion, that the lower level wind shear and lower level jet in the parent environment is increasing rapidly. And then again, here's the proof of that, which I skipped ahead to show you earlier. And then let's go back to mesoscale. Remember, it's obvious by this time that the northern supercell is fried, but the southern supercell is still wide open. Let's focus mesoscale, zoom in on a mesoscale point of view of the southern supercell. So here, At about the time of the last tornado, so the last tornado that the northern supercell produced was an EF2 near the town of Valley City. And obviously that didn't last too long and obviously dissipated quickly because of stable air from the southern supercell's forward-flank downdraft that was being put into the northern supercell over and over again. So stable air in the inflow region kills tornado potential and entirely causes it to lose its identity. However, the southern supercell is still wide open, and it actually, unsurprisingly, produced its own tornado at about 310 UTC. This tornado was an EF2 near the town of Fort Ransom that thankfully kind of turned away and didn't really do too much bad damage. Let's look at this tornado mesoscale-wise. So this is when the Fort Ransom tornado was at its strongest. You can see southern supercells here, northern supercells fried, northern supercells irrelevant. We don't care about the northern supercell anymore. It's obviously not going to do anything tornadic. However, as the supercell dissipates, let's zoom out. We will come back to this image later, so keep an eye. This is the southern supercell, or the situation at the time of the Fort Ransom tornado. So you can see the southern supercell here, northern supercell is dead, and then you can see the line kind of beginning to approach. One important thing to note is that the line is moving so much faster than these two supercells are. We will come back to this image in a moment. Let's go back to the mesoscale stuff of the southern supercell. After that tornado dissipated, though, it seems that the southern supercell kind of began to become disorganized, and it did begin to become disorganized because of this. You see that convective blob right there? That was the beginning of a new updraft that would go into the southern supercells. It'll go up in the southern supercell's inflow region and result in a merger that significantly enhanced the intensity of the supercell. Look at this merger in action. This is the beginning of that merger, and then it goes up. That merger significantly intensified, and the supercell still looks disorganized because the merger hasn't fully happened yet, but by 341, the merger completely happened. Look at that difference. Look at this 13-minute difference. It already looks much better, and as the two supercells begin to merge, it just significantly enhanced the intensity of the storm, and that made this southern supercell look better and better. Compare it before, and then the merger begins. Merger still processing the merger, and the merger is complete by this point. Look at that difference. You can see this supercell is far healthier than this one at the time that the Fort Ransom tornado dissipated. So that is one thing. One mesoscale thing that happened right before the formation of the Enderlin tornado was that extremely favorable merger that significantly boosted the intensity and the health of the southern supercell. Another thing that happened is, look at this. This is right as the Enderlin tornado was forming. Look right here. There is a secondary cell just south of the tornado and mesocyclone. So here's the tornado and mesocyclone, and right here you have another cell just south of it. That cell is acting as a nudger and is significantly influencing this mesocyclone's intensity. Why? Every convective cell, no matter how size, has some sort of downdraft. If you put that downdraft right next to an updraft, because remember, a tornadic mesocyclone is an updraft. If you put a downdraft next to an updraft, like the laws of physics and meteorology will just tell you that will significantly increase the updraft's intensity, because the significant differences between the two means that air will rush from the downdraft directly into the updraft, and it will boost the updraft's intensity as a result. Also, this nudger is placed in a way that it is not dropping stable air into the supercell's inflow region, which is further enhancing the effectiveness of this merger. So not only mesoscale-wise did we have a favorable merger significantly boost the supercell's intensity, we had a nudger storm in perfect position, put an updraft right next, which put a downdraft right next to the enhanced supercell's updraft, and significantly boosted the tornadic mesocyclone's intensity. Look at that here. The nudger cell still doesn't begin to shed the inflow region with stable air and remains right next to that tornadic mesocyclone and significantly boosts the mesocyclone's updraft intensity. That's the second mesoscale thing that went right. Remember how I told you to keep in mind where the line was in this image? This is the final mesoscale thing that came together, which allowed the Enderlin tornado to significantly surpass the intensity of the previous tornado the supercell produced and the two tornadoes that the northern supercell produced. So, look at where the line is here. Fast forward. Look at where it is now. It is so much closer. As a line approaches, it pushes air up and above it. It pushes air in the warm sector up and above it and creates a localized area of lift. So, let's look at the Enderlin supercell again and compare it to the previous Jamestown and Valley City supercell and the tornado near Fort Ransom. One, the Enderlin tornado happened last. So that means we've already established way earlier that large scale-wise, the parent parameter space and environment was becoming more favorable for tornado activity because of the LLJ, increasing shear and increasing moisture. Not only that, but in the minutes between the Fort Ransom tornado and the Enderlin tornado, the southern supercell underwent a favorable merger that significantly boosted its intensity. Not only that, but mesoscale-wise, because the merger was a mesoscale thing, another mesoscale thing happened. Another mesoscale thing came into place, with a perfectly placed nudger cell, which significantly increased the tornadic mesocyclone's updraft intensity, without putting stable air into the inflow, significantly increasing tornado genesis odds, and third, you had just a little bit of enhanced lift coming from the approaching line, which may further serve to intensify the tornadic mesocyclone's updraft. Those three mesoscale things, large scale, parent environment was becoming more favorable, and mesoscale, the southern supercell was still wide open, had a perfectly placed nudger, underwent a merger to significantly boost its intensity, and was getting struck from the line. That's why the tornado that this supercell would begin to produce right now, the Enderlin, North Dakota tornado, reached such an incredible intensity. That's why this supercell was able to produce an EF5. Just to recap, the background environment was becoming more favorable and was far more favorable when the Enderlin tornado formed than at the time of any of the prior tornadoes. And not only that, but mesoscale, so many things went right for the parent supercell to create a perfect combination to get a tornado of EF5 caliber intensity. It should be no surprise that a tornado of that intensity actually ended up happening meteorologically, and meteorologically, I think that this event makes a lot of sense to me. Thank you for watching, and I hope you found this video helpful.